12 human beings have stood on the surface of the moon. No atmosphere above them, no light pollution, no clouds, nothing between them and the rest of the universe, but empty space. If there is anywhere a human being should be able to see the full, unfiltered sky, every star in every direction blazing without interference, it is there. The photographs they took show a black sky, completely, absolutely black, not a single star. For decades, that fact alone has been handed to conspiracy theorists like a gift. If the moon landing was real, they ask, where are the stars? But here is what makes this genuinely strange, and it has nothing to do with conspiracy. The same astronauts who appear in those starless photographs, also described in their own words, in mission transcripts, looking up and seeing the stars, sharp, clear, everywhere, the same place, the same sky, one version completely empty, one version full. Both are true, and the reason they can both be true at the same time is one of those things that once you understand it, changes the way you see photographs, cameras, and your own eyes permanently. Today, we get into it. We make these long-form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe, and we'll be here whenever you need a quiet journey through the cosmos. It starts with how light actually reaches us. We begin not with space, but with the quiet mechanics inside your own eyes, the instruments you carry without noticing, adjusting constantly as light shifts around you. Vision is not passive, it is an active negotiation with light. Inside the retina love two kinds of cells. Cones handle color and fine detail in bright conditions, while rods take over in darkness, built for sensitivity rather than precision. There are about 120 million rods and 6 million cones in each human eye, a balance that favors detecting faint light over sharp clarity when illumination fades. Rods are remarkably delicate. A single photon, the smallest unit of light, can trigger a response, but this sensitivity comes at a cost. They require time to awaken. When you step into darkness, they slowly recalibrate in a process called dark adaptation, meaning the gradual increase in visual sensitivity over several minutes as chemical changes restore their function. At the same time, the pupil expands. In bright light, it narrows to about 2 millimeters, restricting incoming light to protect the retina. In darkness, it opens to roughly 8 millimeters, allowing up to 16 times more light to enter. This widening is immediate, but it is only part of the adjustment. True night vision takes patience, but even at its best, your vision is dynamic, constantly shifting exposure without conscious control. A camera cannot do this in the same way. A camera must decide before it sees. It relies on 3 fixed settings. Shutter speed controls how long light reaches the sensor. Aperture defines how wide the lens opens. ISO determines how sensitive the sensor is to incoming light. Together, these form the exposure triangle, a system where each setting balances the others to produce a usable image. Change one, and the rest must follow. A longer shutter gathers more light, but risks blur. A wider aperture brightens the scene, but reduces depth. A higher ISO amplifies faint signals, but introduces noise. Every photograph is a compromise. In bright environments, the camera compresses this triangle to prevent overwhelming the sensor. Exposure times shorten, apertures tighten, sensitivity lowers. The goal is clarity in intense light, preserving detail in surfaces illuminated by the sun. But this adjustment comes with a hidden consequence. Faint light vanishes. Stars, even the brightest ones, are extraordinarily dim compared to sunlit objects. The difference is not subtle. It is vast beyond everyday intuition. When a camera exposes for a reflective astronaut suit or the lunar surface, It effectively closes the door on everything weaker. The stars are still there. The sensor simply cannot register them under those conditions. This is not a flaw. It is a limit built into every imaging system, including your own eyes. Both operate within a finite range of brightness, a concept known as dynamic range, meaning the span between the darkest and brightest details that can be perceived at once, and it is within that narrow window that all visible reality must fit. A useful way to understand the problem is to assign numbers to light itself, to treat brightness not as a feeling, but as a scale we can measure and compare. Photographers use a unit called an f-stop, which simply means a doubling or halving of light with each step. One step brighter, twice as much light. One step darker, half as much. This scale grows quickly. It stretches far beyond everyday experience, but the sky operates on a much larger range than any human system comfortably handles. The Sun, as seen from Earth's orbit, has an apparent magnitude of negative 26.7, a logarithmic measure of brightness, where lower numbers mean brighter objects. Sirius, the brightest star in the night sky, sits at negative 1.46. The difference appears small in notation, yet it represents a gap of about 25 magnitudes. That gap is immense. It corresponds to roughly 10 billion times more light. Now place a camera into this imbalance. Imagine it pointed at a sunlit astronaut suit, reflecting between 70 and 85% of incoming sunlight, a surface designed to protect and regulate temperature under direct exposure. The camera must reduce incoming light drastically to avoid overwhelming its sensor. Shutter speeds shorten to fractions of a second, apertures narrow, sensitivity drops, the bright surface is preserved, everything else fades. At those settings, a distant star becomes almost irrelevant. For a star to register clearly under the same exposure, it would need to be about 10,000 times closer than it actually is. Otherwise, its light falls below the sensor's threshold, too weak to leave a measurable trace. But this is not a limitation unique to a specific device or mission. It is built into the physics of detection. Every camera ever constructed, from early film to modern digital sensors, faces the same constraint when confronted with such extremes. The limitation has a name: dynamic range. Dynamic range describes the span between the brightest and dimmest details that a system can capture in a single exposure. It defines what can coexist in one image without losing information. Outside that span, data is either blown out or disappears entirely. Human vision performs better, but only within limits. Under ideal conditions, the eye can manage about 21 f-stops of dynamic range through rapid adjustment and neural processing. Modern camera sensors typically handle between 12 and 15 f-stops in a single frame, depending on design and technology. Neither system is wide enough. When confronted with a surface blazing under direct sunlight and stars that whisper across unimaginable distances, something must give. The system chooses the brighter subject because it dominates the available signal. The faint light is not blocked or removed. It is simply overwhelmed. So the image resolves into what the sensor can hold, and what lies beyond that boundary slips quietly out of record. Close your eyes for a moment and imagine the sun slipping behind a horizon you cannot see, not setting, but simply moving out of view as you drift into shadow. The brightness falls away almost instantly. What remains is not empty, but something else happens first. Your eyes begin to adjust again, repeating that slow internal shift, reopening sensitivity that had been suppressed under direct light. In orbit, this transition can take only minutes, and once it completes, the sky reveals itself with a clarity that has no equivalent on the ground. Astronaut Chris Hadfield described this moment from the cupola of the International Space Station during orbital night, when Earth blocks the sun completely. He reported seeing more stars than at any point in his life, a dense field of points that did not flicker or shift, but held steady in perfect stillness. The difference is immediate. There is no atmosphere between you and the light. On Earth, starlight passes through layers of moving air. Tiny fluctuations in temperature and density bend the light repeatedly, creating the familiar twinkling effect. This process is called atmospheric turbulence, meaning the constant motion of air that distorts incoming light. In orbit, that distortion is gone. Each star appears as a fixed, sharp point. The sky becomes structured, not decorative, but precise. But the experience changes again during spacewalks, when astronauts move outside their spacecraft and orient themselves away from the sun. With direct light removed from their field of view, the contrast deepens further. The Milky Way, often faint from the surface, becomes a visible band with texture and variation, a layered formation stretching across the sky with discernible density. It is not a haze, it has form. During the Apollo missions, astronauts traveling between Earth and the Moon reported something even stranger. At certain points beyond Earth's protective magnetic field, they began to notice brief flashes of light, even when their eyes were closed. These flashes were caused by cosmic rays, high-energy particles moving near the speed of light, passing directly through the retina and triggering visual signals without any external light source. Vision, in that moment, is no longer tied only to what is outside, but when fully adapted and oriented away from intense light, the human eye in space performs at its natural limit. Under ideal conditions, you can see roughly 5,000 stars, similar to what is visible from a clear, dark location on Earth. The difference lies in quality. Each point is sharper, more stable, and more defined against the background. Nothing interferes, nothing scatters. The stars are present, consistent, undiminished. And this is where the divide becomes undeniable. The images remain empty, but the experience does not. The absence in photographs does not reflect absence in reality. It reflects the boundary between what can be recorded and what can be directly perceived, a boundary that shifts depending on how and where you look. The doubt did not begin in laboratories or observatories. It began in living rooms, in quiet moments when people studied photographs and noticed something that felt wrong, a sky that seemed incomplete in a place where nothing should have hidden it. The absence stood out more than anything present. By the mid-1970s, this detail had found a voice. Bill Kaysing, a former employee of Rocketdyne, published a book in 1976 titled "We Never Went to the Moon," arguing that the missions had been staged. Among his claims, the missing stars became central. If the moon has no atmosphere, he reasoned, then thousands of stars should fill the sky. Their absence, he suggested, pointed to artificial lighting and a constructed scene. At first glance, the argument feels consistent. It follows a line of logic that seems grounded in observation. You expect the sky to reveal more when nothing stands in the way. When it does not, the simplest explanation can feel like deception. But this is where understanding replaces assumption. The answer rests in the same system that governs every photograph, the balance between shutter speed, aperture, and sensitivity that determines how light is recorded. When photographers describe this balance, the reasoning behind those Apollo images becomes clear. The camera was not ignoring the stars, it was prioritizing something else. To capture astronauts and the lunar surface under direct sunlight, exposure had to be reduced sharply. Light reflecting from the moon is intense, far brighter than most people expect. Without atmospheric filtering, sunlight strikes the surface and returns with little loss. The camera adjusts accordingly, shortening exposure time and narrowing its intake of light. In doing so, it excludes the faint. But this principle is not theoretical. It has been tested directly. In 2008, the television program Mythbusters recreated Apollo-era conditions using comparable equipment and lighting. They photographed a brightly lit subject against a dark background, carefully controlling exposure settings to match those used on the moon. Because of detail, in every test, the stars disappeared from the image. The outcome was consistent, predictable. What seemed like a contradiction turned out to be confirmation. The blank sky was not evidence of absence, nor of fabrication. It was evidence of brightness, of a surface reflecting unfiltered sunlight in an environment without atmospheric diffusion. The moon, in that sense, revealed itself through the limitation, but the deeper point is more subtle. The observation was valid. The reasoning was incomplete. A real phenomenon had been identified, yet its cause was misunderstood. This is how perception can diverge from reality, not through lack of attention, but through missing context. And once that context is restored, the image does not change, only the meaning does. Instead of reducing light, we can do the opposite. We can allow it to accumulate, slowly, patiently, letting faint signals build until they rise above the threshold of detection. This approach is called long exposure, meaning the sensor remains open for extended periods, gathering photons that would otherwise pass unnoticed. Remove the bright surface from view, and the balance shifts. Without overwhelming light dominating the frame, the camera no longer needs to restrict itself. Shutter times lengthen. Sensitivity increases. The faint begins to register. But the transformation is not gradual. It is immediate. Stars appear first, scattered points returning to visibility. Then more follow, filling regions that once seemed empty. Given enough time, the sky changes character entirely, revealing structure where nothing had been recorded before. This principle was demonstrated with extraordinary precision in 1995 when the Hubble Space Telescope was directed toward a region near the constellation Ursa Major, close to the Big Dipper. The selected area appeared blank through ground-based observation, a dark patch without notable features. Its size in the sky was tiny, roughly equivalent to a grain of sand held at arm's length. Hubble did not move. It remained fixed on that single point for 10 consecutive days, accumulating about 100 hours of exposure. Each photon that arrived was recorded, no matter how faint, building a composite image over time. What emerged was not emptiness, it was density. The final image contained approximately 3,000 galaxies, each composed of vast collections of stars, some extending back billions of years into cosmic history. Objects that had never been seen before appeared in a field once assumed to hold nothing at all. The sky had not changed. The method had. But this process is not limited to large observatories. On Earth, amateur astrophotographers use the same principle with accessible equipment. By extending exposure to several minutes, sometimes stacking multiple images together, they capture nebulae, star clusters, and distant galaxies that remain invisible to unaided vision. Time becomes the key variable, not location, not scale. This approach expanded further with the launch of the James Webb Space Telescope on December 25, 2021. Unlike earlier instruments, it observes primarily in infrared, meaning wavelengths longer than visible light that human eyes cannot detect. These wavelengths reveal objects obscured or shifted beyond optical range. In July 2022, Webb released its first deep field image, focusing on a similarly small region of sky. The results showed galaxies from approximately 13.1 billion years ago, their light stretched and preserved across cosmic time, gathered through sustained observation. Each layer added depth, each exposure revealed more. But the pattern has remained consistent. Every region of sky studied with sufficient exposure has yielded more structure than expected across every direction and scale. No truly empty field has been confirmed. The darkness, it turns out, responds to patience. Imagine tuning a radio but leaving the dial fixed on a single narrow frequency, unaware that countless other signals pass through the same space, silent only because the receiver cannot shift. This is how vision operates, not as a complete system, but as a narrow channel within a much larger field of information. What we call light is only a fragment. It belongs to a broader structure known as the electromagnetic spectrum, meaning the full range of energy waves that travel through space at the speed of light. These waves differ only in wavelength, which is the distance between peaks in the wave. Some stretch for kilometers, others are smaller than the nucleus of an atom. Visible light occupies a small interval within this range. It spans wavelengths from about 380 nanometers, which we perceive as violet, to roughly 700 nanometers, which we perceive as red. That is a total span of 320 nanometers, a thin slice within a spectrum that extends from 1/4 of a meter to 100 million meters. The scale difference is vast. It covers 23 orders of magnitude. But when we calculate the portion accessible to human vision, the result becomes even more striking. Visible light represents approximately 0.0035% of the total electromagnetic spectrum, far less than 1/100%. Everything we have ever seen with our eyes exists within that narrow band. The rest is not absent. It is simply unobserved. In radio wavelengths, which have long waveforms measured in meters to kilometers, the sky behaves differently. The Milky Way emits strongly, forming patterns that bear little resemblance to its visible appearance. Pulsars, rotating neutron stars, produce pulses of radio waves with extreme regularity, acting like precise cosmic clocks. Remnants of exploded stars continue to broadcast signals across thousands of light years. Shift to infrared, and another layer emerges. Infrared refers to wavelengths longer than visible red, associated with heat emission. Objects too cool to glow visibly, including many low-mass stars, become prominent. Dense clouds of gas and dust that block visible light turn transparent, revealing regions where stars are forming within hidden structures. But move further, and the environment changes again. In the X-ray portion of the spectrum, which consists of extremely short wavelengths and high-energy radiation, the sky becomes violent. Material falling into black holes heats to millions of degrees, emitting energy at levels invisible to human perception. These emissions trace the most energetic processes in the universe. None of this is speculative. It required new instruments to detect. But for most of human history, these wavelengths were unknown. Until the 20th century, observation remained confined to visible light alone. Every map of the sky, every theory of structure, every assumption about the universe was based on less than 0.004% of available information. And yet, from that narrow window, we believed we were seeing everything. The discovery did not begin with a telescope pointed upward, but with a problem on the ground, a persistent interference that refused to disappear no matter how carefully it was traced. In 1931, an engineer named Carl Jansky, working at Bell Laboratories in New Jersey, was tasked with identifying sources of radio static that affected transatlantic communication. He built a rotating antenna designed to isolate signals by direction and began listening. What he found did not behave like local noise. The signal rose and fell in strength with a regular rhythm, peaking once every 23 hours and 56 minutes. That interval did not match the solar day, which is based on the sun's position and lasts 24 hours. It matched sidereal time instead, meaning the rotation of Earth relative to distant stars. The source was not on Earth. It was beyond the solar system, fixed against the background of the sky. But Jansky did not set out to study the cosmos. He had, without intending to, detected radio waves from the center of the Milky Way, the first confirmed observation of cosmic radio emission. The sky, it seemed, was not silent. Others followed. In 1937, an amateur radio enthusiast named Grote Reber constructed the first purpose-built radio telescope in his backyard in Illinois. It was a parabolic dish, 9.4 meters in diameter, shaped to collect and focus radio waves onto a receiver. Over several years, he scanned the sky systematically, recording intensity and direction. His maps revealed a structure that did not match anything seen in visible light. The galaxy appeared luminous in regions that looked dark to the eye, while familiar bright stars contributed little to the signal. The distribution of energy had no simple correspondence with optical observation, but the most striking discoveries came later. In 1967, at the University of Cambridge, a young researcher named Jocelyn Bell Burnell detected a series of repeating radio pulses while analyzing data from a large antenna array. The pulses were precise, arriving at intervals measured in fractions of a second with remarkable consistency. The regularity was so exact that, for a brief time, the possibility of an artificial origin was considered. The signal was labeled LGM-1, short for Little Green Men. But further observation revealed a natural source. These signals came from pulsars, which are rotating neutron stars, the collapsed cores of massive stars that ended their lives in supernova explosions. A neutron star compresses more mass than the Sun into a sphere, only about 20 kilometers across. As it spins, it emits beams of radiation from its magnetic poles. If one of those beams crosses our line of sight, it appears as a pulse. Some rotate slowly, others are extraordinarily fast. The fastest known pulsar, designated PSRJ 1748-2446 AD, completes 716 rotations every second. At that rate, its equator moves at roughly 24% of the speed of light. What began as interference became a new sense. The sky was speaking all along. If you could feel the sky instead of seeing it, the darkness would change again, because every object with any temperature at all releases energy as heat. This emission is called infrared radiation, meaning light with wavelengths longer than red, invisible to your eyes but present everywhere. Nothing is exempt. Even the coldest objects glow. But the cooler something is, the longer the wavelength it emits. This shift moves its signal out of the visible range and into infrared, where detection requires instruments tuned to those frequencies. Stars that appear dim or invisible light can become prominent when observed this way, especially those with surface temperatures below about 2,500 Kelvin. These stars, often red dwarfs, dominate the galaxy by number. They burn slowly, quietly, and efficiently, producing most of their energy outside the range you can see. In infrared surveys, they emerge in vast quantities, filling regions that seemed sparse when viewed through optical telescopes. But not all objects reach even that threshold. Brown dwarfs exist in the boundary between planets and stars, with masses too low to sustain hydrogen fusion in their cores. For decades, they remained theoretical, predicted by models, but unconfirmed by observation. That changed in 1995 when infrared instruments finally detected them directly. Their temperatures are low compared to stars, and their light is almost entirely emitted in infrared wavelengths. Since then, estimates suggest there may be between 100 billion and 400 billion brown dwarfs in the Milky Way alone. None are visible to the human eye, but infrared does more than reveal individual objects. It changes how we understand structure. Between 2003 and 2020, the Spitzer Space Telescope surveyed the galaxy in infrared light, mapping regions hidden behind dense clouds of dust. These clouds block visible wavelengths completely, making large portions of the galaxy opaque to traditional observation. Infrared passes through. It uncovers what lies within. Spitzer's data revealed that the Milky Way has two primary spiral arms, not four as previously believed, a correction made possible only by observing beyond visible light. The structure of our galaxy was not different. Our view of it was incomplete. But the most profound shift occurs in regions where stars are born. Star formation takes place inside cold, dense clouds of gas and dust, environments that appear completely dark when viewed optically. These clouds absorb visible light, hiding everything inside. In infrared, they become transparent. Within them, new stars ignite. The Orion Nebula offers a clear example. To the naked eye, it appears as a faint, diffuse patch in the constellation Orion, with a small cluster of bright stars known as the trapezium at its center. But when observed in infrared, that same region reveals hundreds of young stars at various stages of formation, embedded within the cloud that created them. What looked sparse becomes crowded. What seemed still becomes active. The sky, once again, changes not by moving, but by being seen differently. If you could peel away the protection of air above you, the sky would change in a way that no eye could endure. Because some forms of light carry so much energy, they tear through living tissue before they ever reach awareness. These are X-rays, a region of the spectrum defined by extremely short wavelengths and high-energy photons. Earth's atmosphere absorbs them almost completely. This shielding is what allows life to exist at the surface, but it also kept this part of the universe hidden until instruments were lifted beyond the air itself. But once that boundary was crossed, the view transformed quickly. In 1970, the first dedicated X-ray telescope, named Uhuru, was placed into orbit. Within its first year, it cataloged 339 distinct X-ray sources across the sky, many of them unlike anything previously observed. Among these detections was Cygnus the 10th one, located about 6,070 light-years from Earth. It is a binary system, meaning two objects orbit each other, one visible and one unseen. The visible member is a blue supergiant star, massive and luminous. The companion cannot be seen directly, yet its gravitational influence is unmistakable. Its mass is about 21 times that of the Sunday. No known object, other than a black hole, can explain that combination of mass and invisibility, but the evidence goes further. Material from the visible star is being pulled toward the unseen companion, forming a structure called an accretion disk, which is a rotating ring of gas spiraling inward under gravity. As this material compresses and accelerates, it heats to millions of degrees. At such temperatures, it no longer emits visible light. It radiates in X-rays, releasing energy that can only be detected by instruments designed for that range. This is how black holes announce themselves. But Cygnus 10.1 is not unique. Across the X-ray sky, similar processes unfold continuously. Neutron stars collide, galaxy clusters interact, and matter falls into deep gravitational wells with extreme force. The sky that appears calm in visible light is revealed as a network of high-energy events, each releasing vast amounts of radiation. The scale is difficult to grasp. The intensity is constant. In 1999, the Chandra X-ray Observatory was launched to study these phenomena with unprecedented clarity. Its resolution is so precise that it can distinguish details comparable to reading a newspaper at half a mile distance, but in X-ray wavelengths. One of its most detailed observations focused on the aftermath of a stellar explosion recorded in 1987, known as SN 1987A, located in the Large Magellanic Cloud. Over decades, Chandra tracked the expanding shockwave as it interacted with surrounding gas, lighting up rings of material that had been ejected before the explosion. For the first time, a supernova's aftermath was observed evolving on a human timescale. But what this reveals is not just motion. It reveals intensity. The processes shaping the universe are not gentle. They involve compression, collision, and release of energy at scales far beyond ordinary experience. We do not see this directly because our eyes are not tuned to those wavelengths. The stillness we perceive is selective, and beneath that selection, the sky is constantly in motion, defined not by silence, but by energy we were never meant to see. There is a band of light just beyond what you can see, close enough to touch the edge of vision, yet entirely inaccessible, without protection or instruments. This is ultraviolet, a region of the spectrum defined by wavelengths shorter than visible violet, extending from about 10 to 400 nanometers. The sun produces it constantly. Roughly 10% of its total energy leaves in this form. But most of that energy never reaches you. Earth's ozone layer absorbs the most energetic portion, known as UVC, meaning ultraviolet radiation at the shortest wavelengths. Without this filtering layer, the surface of the planet would be exposed to radiation strong enough to break molecular bonds in biological tissue, gradually sterilizing exposed environments over relatively short timescales. Life depends on that absorption. Vision depends on its absence. But when we move observation above the atmosphere, the ultraviolet sky becomes accessible, and what appears changes again. The distribution of brightness no longer matches what you expect from visible light. Stars that dominate the night sky visually may contribute little in ultraviolet, while others become prominent for the first time. The hottest stars lead this shift. O-type and B-type stars, which are large, massive, and extremely hot, emit most of their energy at ultraviolet wavelengths. Their surfaces reach tens of thousands of Kelvin, pushing their peak emission beyond visible range. In ultraviolet surveys, these stars stand out with intensity, even when they appear modest to the eye. But the pattern extends further. Between 2003 and 2013, the Galaxy Evolution Explorer, known as GALEX, mapped the ultraviolet sky in detail. Its observations revealed entire galaxies that appeared inactive in visible light, showing no clear signs of ongoing star formation. In ultraviolet, those same galaxies were active. New stars were forming in regions previously thought quiet, their energy output hidden from optical instruments, but clearly visible at shorter wavelengths. The process had been there all along. But ultraviolet also reveals the later stages of stellar life. White dwarfs, which are the dense cores left behind after stars like the Sun exhaust their fuel, emit strongly in ultraviolet despite appearing faint in visible light. Their surfaces are extremely hot, even as they slowly cool over billions of years. One example lies relatively close to Earth. Van Maanen's star, located about 15 light-years away, is one of the nearest white dwarfs. In visible light, it is difficult to distinguish. In ultraviolet, it becomes far more pronounced. The sky reorganizes under this shift. Familiar constellations lose their shape as dominant stars fade and previously unnoticed sources emerge. The pattern you recognize dissolves into a different arrangement, defined not by brightness in visible light, but by energy at wavelengths your eyes cannot register. But this is not a different universe. It is the same one, viewed through a different threshold. And once that threshold moves, the structure you thought you knew rearranges itself without warning. The signal was not directional. It did not rise from a single point or fade when the antenna turned away. It filled every angle equally, a steady background that refused to disappear no matter where the instrument was aimed. In 1964, Arno Penzias and Robert Wilson at Bell Laboratories in New Jersey were trying to refine a large horn antenna for satellite communication, eliminating sources of interference one by one. But this noise would not yield. It remained constant. They checked everything within reach. Equipment was recalibrated. Components were replaced. Even the interior of the antenna was inspected for contamination. At one point, pigeons had nested inside, leaving behind debris that seemed a likely cause. The antenna was cleaned thoroughly. The signal persisted, unchanged. It came from everywhere at once. But the pattern carried a clue. Its intensity did not vary with local conditions, nor did it match any known terrestrial source. What they were measuring was not interference in the ordinary sense. It was radiation arriving uniformly from the sky, independent of direction or time of day. What they had found was the cosmic microwave background, often abbreviated as CMB, meaning a field of microwave radiation that fills the universe uniformly. It is the oldest light that can be observed, originating from a time long before stars or galaxies existed. To understand its origin, we move backward to an earlier state. In the first few 100,000 years after the beginning of the universe, conditions were extremely hot and dense. Matter existed as a plasma, a state in which electrons and protons were not bound together, but moved freely in a charged, opaque mixture. Photons could not travel freely through this environment. Each attempt to move was interrupted by constant interaction, absorption followed by re-emission, trapping light within the plasma. The universe, at that stage, was effectively opaque. But as expansion continued, temperature dropped. Around 308,000 years after the beginning, the average temperature fell to about 3,000 Kelvin. At that point, electrons combined with protons to form neutral hydrogen atoms. This transition reduced scattering dramatically. Light was released. The universe became transparent. That light has been traveling ever since. But over billions of years, as space itself expanded, the wavelengths of that radiation stretched. What began as visible or near visible light shifted gradually into longer wavelengths, moving into the microwave region of the spectrum. Today, it fills the sky with a nearly uniform temperature of 2.725 Kelvin, just above absolute zero. It is present in every direction, but it cannot be seen. Human vision does not extend into microwave wavelengths, and optical instruments do not detect it. Yet if a receiver is tuned appropriately, the entire sky glows with this faint signal, a remnant of a time when light first moved freely through space. Even on Earth, traces of it have been encountered unknowingly. About 1% of the static seen on an analog television tuned to no channel comes from this background, a faint residue of early cosmic conditions embedded in everyday noise. The signal never left, it only changed form. If you measure a system by how it moves, rather than how it looks, a different kind of structure begins to appear, one that cannot be seen directly, but reveals itself through influence alone. Gravity becomes the tool, tracing mass that does not shine. In 1933, Swiss astronomer Fritz Zwicky applied this approach to the Coma Cluster, a collection of roughly 1,000 galaxies located about 320 million light-years away. He estimated the total mass of the cluster by measuring its luminosity, meaning the combined light output of all its visible components. Then he calculated how much mass would be required to keep those galaxies gravitationally bound based on their observed speeds. The result did not align. The galaxies were moving too fast. The visible matter was not enough. The discrepancy was large, about a factor of 400. According to the numbers, the cluster should have dispersed long ago, yet it remained intact. Zwicky concluded that additional mass must be present, unseen but exerting gravitational influence. He called it dunkel materie, or dark matter. But the idea did not take hold immediately. It remained largely unaccepted for decades. But in the 1970s, a second line of evidence emerged. Astronomer Vera Rubin began measuring rotation curves in spiral galaxies, tracking how orbital velocity changes with distance from the center. A rotation curve is simply a plot of how fast stars move at different radii. Under classical expectations, based on Newtonian gravity, stars farther from the center should move more slowly, similar to planets in the outer solar system. The gravitational pull weakens with distance, so orbital speeds should decline. But the data did not follow that pattern. Instead, stars in the outer regions were moving at nearly the same speed as those closer in. In some cases, they were moving even faster. The rotation curves flattened out, remaining constant across large distances where they should have dropped. This behavior could not be explained by the visible mass alone. The only consistent solution was the presence of an extended halo of unseen matter surrounding each galaxy, contributing additional gravitational pull. The structure was there. It simply did not emit light. Dark matter does not interact with electromagnetic radiation. It does not absorb, reflect, or emit any wavelength, from radio waves to gamma rays. Its presence is inferred entirely through gravity, through the way it shapes motion and structure on large scales. But its influence is dominant. Current estimates suggest that dark matter accounts for about 27% of the total energy content of the universe. By comparison, all visible matter, every star, planet, cloud of gas, and galaxy ever observed, contributes only about 5%. The rest remains unlit. What you see is not the framework. It is what settles within it. The measurement began with distant explosions, brief events that outshine entire galaxies and then fade, leaving behind a trace that can be compared across vast distances. These events are called Type Ia supernovae, meaning stellar explosions that occur under nearly identical conditions, producing almost the same intrinsic brightness each time. Because of this consistency, they serve as standard candles, which means objects of known luminosity used to measure distance by comparing how bright they appear. The dimmer they look, the farther away they are. This method allows us to map expansion itself. In 1998, two independent teams, the Supernova Cosmology Project and the High Z Supernova Search Team, applied this technique to measure how the universe changes over time. They observed supernovae at different distances, effectively looking back across billions of years to track how fast space was expanding at earlier stages. The expectation was clear. Gravity, acting across all matter, should slow the expansion gradually, pulling galaxies back toward each other. Over time, that expansion rate should decrease. But the data refused to follow that pattern. The distant supernovae appeared dimmer than predicted, not because they were intrinsically different, but because they were farther away than expected under a slowing expansion. The only consistent interpretation was that expansion had not slowed. It had increased. The universe was accelerating. But this result was not accepted immediately. Both teams spent months verifying their measurements, checking instruments, recalibrating assumptions, and searching for alternative explanations. The conclusion remained unchanged. Something was driving space apart. This influence was not tied to matter in the usual sense. It did not cluster, form structures, or emit detectable radiation. Instead, it appeared to be a property of space itself, a kind of energy embedded uniformly throughout the cosmos. As space expands, more of this energy comes into existence, maintaining a constant density even as volume increases. This behavior creates a repulsive effect on large scales, counteracting gravity and eventually dominating it. The expansion does not just continue, it accelerates outward. This phenomenon was named dark energy. But unlike earlier discoveries, it is not associated with a specific object or region. It is present everywhere, shaping the evolution of the universe as a whole. Current estimates suggest it accounts for about 68% of the total energy content of the cosmos. When combined with dark matter, which contributes about 27%, the proportions become clear. All forms of visible matter, every structure detected through light or direct observation, represent only about 5% of what exists. The remaining 95% has not been directly observed, but its effects are measurable. Its influence is unavoidable. The expansion you inhabit is not slowing. It is being driven outward by something that does not shine, does not cluster, and does not reveal itself except through the motion it imposes on everything else. There is a simple rule that governs how light fades, one that applies everywhere without exception, shaping what you can see long before instruments or biology impose their limits. It is called the inverse square law, meaning that brightness decreases with the square of distance. Move twice as far away from a light source, and its apparent brightness drops to 1/4. Move 3 times farther, and it falls to 1/9. The pattern continues, each step outward, reducing intensity faster than intuition expects. But in space, distance grows quickly. The nearest star beyond the Sun is Proxima Centauri, located about 4.24 light-years away, which is roughly 40 trillion kilometers. Light travels at 299,792 kilometers per second. Yet even at that speed, it takes more than 4 years to reach you. What you see tonight left that star years ago. But Proxima Centauri is not a bright star. It is a red dwarf with about 12% of the Sun's mass and roughly 0.17% of its luminosity, meaning the total energy it emits. Even though it is the closest stellar neighbor, it is too faint to be seen with the naked eye from Earth. Distance reduces its signal below visibility, but this effect becomes far more extreme as we look outward. In 2022, astronomers using the James Webb Space Telescope identified a galaxy designated HD1 with an estimated distance of about 33.4 billion light-years. This number does not represent travel time alone, because the universe has been expanding while the light was in transit, stretching the distance continuously. The path itself changed during the journey. By the time that light reached the telescope, its intensity had been reduced to a level barely distinguishable from background noise. Detection required instruments operating above the atmosphere, using long exposure times to accumulate faint signals over hours. Even then, the galaxy appears only as a small cluster of pixels. But the law remains consistent. Every photon spreads outward as it travels, covering a larger area, reducing its concentration at any single point. No matter how bright the source, sufficient distance will diminish it below detection thresholds. This is not a failure of observation. It is a consequence of geometry. But consider the implication. Every star, every galaxy, no matter how luminous, becomes invisible beyond a certain range unless detection methods adapt to compensate. The universe is filled with light that simply arrives too diluted to register. The darkness you see is not an absence of emission. It is a boundary defined by distance, where signals fall below the sensitivity of the systems observing them. And that boundary moves only when the method changes, not when the light itself disappears. There's a question that seems almost too simple to matter, one that could be asked by anyone looking up on a clear night. If stars fill the universe in every direction, why is the sky not completely bright? Why does darkness remain between them? In 1823, the German astronomer Heinrich Wilhelm Olbers gave this question its most famous form, though the idea had appeared earlier in the work of Edmund Halley in 1720 and Jean-Philippe Loys de Chezeaux in 1744. The reasoning is direct. In an infinite universe, filled uniformly with stars, every line of sight should eventually end on the surface of a star. There should be no gaps, no darkness. Each point in the sky would correspond to a distant stellar surface, and the combined effect would produce a brightness comparable to the sun itself. The entire sky would glow continuously, leaving no contrast between night and day. But that is not what you see. The sky remains dark, even under ideal conditions, even far from artificial light. The contradiction between expectation and observation is known as Olbers' paradox, meaning a logical conflict between a simple model and the actual appearance of the universe. But the resolution does not come from a single correction. It comes from several layers of understanding that were not available when the question was first asked. In 1848, long before modern cosmology took shape, Edgar Allan Poe proposed an answer in his prose work, Eureka. He suggested that the universe has a finite age, and that light from the most distant stars has not yet had time to reach us. This insight aligns with what is now measured. The universe is approximately 13.8 billion years old. Light travels at a finite speed, so there is a limit to how far it can have moved since the beginning. This limit defines a boundary called the cosmic horizon, meaning the maximum distance from which light has had time to arrive. Beyond that horizon, light exists but has not reached you. But even within that boundary, another effect reduces visibility. As space expands, it stretches the wavelength of light traveling through it. This process is called redshift, meaning the shifting of light toward longer wavelengths as distance increases. Over vast distances, visible light can be stretched into infrared, then into microwave wavelengths, moving entirely out of the range your eyes can detect. The light does not vanish. It changes form. So the darkness you see is not a lack of stars. It is the result of limits of time, of distance, and of perception. Some light has not arrived. Some has been shifted beyond visibility. Some is simply too faint to register. But the sky is not empty. It is bounded. Beyond that boundary, stars continue to exist in numbers that cannot be counted, emitting light that travels outward but has not yet crossed into the region you can observe, or has already moved into wavelengths your senses cannot follow. Listen to a siren as it passes you on a quiet road, and you notice the pitch change, higher as it approaches, lower as it moves away. This shift is not in the source itself, but in how its waves reach you. The same principle applies to light. But in light, the change appears as color. When a source moves away, its wavelengths stretch, shifting toward the red end of the spectrum. When it moves closer, those wavelengths compress, shifting toward blue. This effect is called the Doppler effect, meaning a change in wavelength caused by motion relative to the observer. In 1929, Edwin Hubble used this principle to study distant galaxies from Mount Wilson Observatory in California. By analyzing their spectra, which is the pattern of light spread into its component wavelengths, he found that nearly all galaxies outside our local group showed redshift, meaning their light had been stretched toward longer wavelengths. The pattern was consistent. The farther a galaxy was, the greater its redshift. But this was not just motion through space. The interpretation went deeper. Space itself was expanding, carrying galaxies with it, increasing the distance between them without requiring them to move through a fixed background. The analogy often used is an inflating surface, where points drift apart as the surface grows. The light traveling through that space stretches along with it. But as distance increases, the effect becomes more extreme. Light that began in the visible range can be shifted entirely beyond what human eyes can detect. Ultraviolet emissions may arrive as visible red light. Visible light may arrive as infrared. Beyond certain distances, even infrared is stretched into microwave or radio wavelengths. The original signal remains. Its form changes. This transformation is measured using a parameter called redshift, often denoted as Z, which describes how much the wavelength has been stretched compared to its original value. A redshift of 2 means the wavelength has tripled. Light that left a galaxy as ultraviolet arrives here as visible red. At higher values, the shift becomes more dramatic. A galaxy observed at a redshift of 10 has had its light stretched to 11 times its original wavelength. Nearly all of its visible and near-infrared emissions are shifted into ranges detectable only by specialized instruments. This is the regime targeted by the James Webb Space Telescope, designed to observe the earliest structures in the universe. But for unaided vision, those objects are gone. The light has not stopped traveling. It has not been absorbed or blocked. It has simply been translated into wavelengths outside the range of human perception. The signal continues, unchanged in origin, altered in form. So when distant galaxies disappear from view, they are not hidden. They are still sending light across space, arriving continuously, but in a spectrum your eyes were never built to interpret. And as distance increases, more of the universe shifts beyond that boundary, not into darkness, but into a different kind of illumination that requires entirely different ways of seeing. There is a limit to how far you can see, not because light stops, but because time and expansion set a boundary on what has had the chance to arrive. This boundary is called the observable universe, meaning the region of space from which light has reached us since the beginning. Its radius is about 46.5 billion light-years in every direction. At first, that number seems inconsistent with an age of 13.8 billion years. Light cannot travel faster than its own speed, so how can it reach so far? The answer lies in expansion. While light was traveling, The space it moved through was stretching, increasing the distance between origin and observer during the journey. What began closer is now far away. But within that volume, the scale becomes difficult to hold in mind. Current estimates suggest there are about 2 trillion galaxies inside the observable region, a number revised upward in 2016 after accounting for faint systems beyond earlier detection limits. Each galaxy contains vast numbers of stars. When combined, the total number of stars reaches approximately 1 septillion, or 1 followed by 24 zeros. This is often compared to the number of grains of sand on Earth, yet even that analogy falls short. There are more stars than grains across every beach and desert combined. But this entire structure exists within a limit. Beyond the observable universe lies a region from which no signal has reached us, and none ever will. This is not due to obstruction, but to the finite speed of light and the ongoing expansion of space. There are regions so distant that light emitted there today will never bridge the gap. We cannot receive it, we cannot detect it. But this does not imply absence. Current cosmological models suggest that space continues beyond the observable boundary, possibly without end. The portion we can see is simply the part that has had time to communicate with us through light or other signals. Everything beyond remains unknown. But if space is infinite, and if the number of possible physical arrangements is finite, then repetition becomes inevitable. Given enough distance, the same configurations of matter must occur again. This idea is formalized in a framework known as the Level 1 multiverse, described by physicist Max Tegmark. In that model, regions beyond our horizon may contain structures identical to those here, including galaxies, stars, and even planetary systems arranged in the same way. But we cannot verify this. The horizon prevents observation. It is not a barrier in space, it is a limit in information. The universe does not end at that boundary. It continues, extending beyond what any instrument can measure or any signal can reveal. What you see is not the whole. It is the portion that has reached you, shaped by time, distance, and the expansion of space itself. Right now, as you sit still, particles are passing through you in numbers so large they are difficult to imagine, arriving without resistance, leaving without trace. They do not slow, they do not scatter, they move, as if matter were almost not there at all. These particles are called neutrinos. Each second, about 65 billion neutrinos from the sun pass through every square centimeter of your body. They come from nuclear reactions deep within the solar core, where hydrogen fuses into helium, releasing energy in multiple forms. Neutrinos are among those products, and once created, they escape almost immediately. But their defining feature is not their origin, it is their behavior. A neutrino has almost no mass, less than 1/millionth that of an electron. It carries no electric charge, and it interacts with matter only through the weak nuclear force, which is a fundamental interaction responsible for certain types of radioactive decay. Because of this, neutrinos rarely collide with atoms. They simply pass through. To illustrate the scale of this transparency, a neutrino could travel through a wall of lead 1 light-year thick and emerge on the other side without interacting with a single atom. Most do. The probability of interaction is so low that detection becomes a challenge of scale. But scientists have found a way. In Antarctica, the Ice Cube Neutrino Observatory uses a volume of ice, 1 cubic kilometer in size, as a detector. Embedded within that ice are 5,160 sensors, positioned at depths reaching 2.5 kilometers below the surface. These sensors are designed to capture brief flashes of light produced when a neutrino does interact, which happens rarely but measurably. In a full year of observation, IceCube detects only a few hundred neutrinos. During that same time, trillions upon trillions pass through unnoticed. In a single second, about 100 trillion neutrinos cross the detector without leaving a signal. The silence is expected, but the few that are detected carry information no other particle can deliver. Light, even at its highest energies, can be blocked by dense matter. The core of a supernova, for example, becomes opaque during collapse. Photons cannot escape immediately. They are scattered, absorbed, delayed. Neutrinos are not. They pass through the collapsing core and travel outward at nearly the speed of light, arriving long before any visible signal. On February 23, 1987, detectors in Japan, the United States, and the Soviet Union recorded a burst of 24 neutrinos over 13 seconds. 3 hours later, telescopes observed the brightening of a supernova in the Large Magellanic Cloud, known as SN 1987A. Those 24 particles were the first neutrinos ever detected from a known source beyond the solar system. They carried direct information from the core of a dying star, 168,000 light-years away. They arrived first. There are events in the universe that do not shine at all, not in any wavelength, not even in forms we have learned to detect, yet they still leave a trace. Not in light, but in motion. Not in brightness, but in the structure of space itself. In 1916, Albert Einstein described this possibility as part of general relativity, a theory that treats gravity not as a force in the usual sense, but as a curvature of spacetime caused by mass and energy. When massive objects accelerate, they do not simply move. They disturb the geometry around them. These disturbances are called gravitational waves, meaning ripples that propagate through spacetime at the speed of light. Einstein believed they would exist, but doubted they could ever be measured. The effect would be too small, the distortions too subtle for any instrument to detect. For nearly a century, that assumption held. But on September 14, 2015, at 5:51 in the morning, Eastern Time, a signal appeared. It lasted 0.2 of a second. The first detection came from a facility in Livingston, Louisiana. 7 milliseconds later, the same signal arrived at a second detector in Hanford, Washington. The timing and shape matched precisely, indicating a single event passing through Earth. The source was distant, about 1.3 billion light-years away. 2 black holes, one with a mass of 29 suns and the other 36, had been orbiting each other in a tightening spiral. As they drew closer, they accelerated, releasing energy not as light, but as gravitational waves. In the final fraction of a second, they merged into a single object, emitting more energy than all the stars in the observable universe combined, but entirely in this non-luminous form. What reached Earth was almost nothing. The distortion in spacetime was on the order of 10 to the minus 18 meters, about 1,000th the diameter of a proton. Detecting such a shift required an instrument of extreme precision. The Laser Interferometer Gravitational Wave Observatory, known as LIGO, uses 2 perpendicular arms, each 4 kilometers long. Laser beams travel back and forth along these arms, reflecting between mirrors suspended by glass fibers thinner than a human hair. When a gravitational wave passes, it stretches one arm and compresses the other by a minuscule amount, altering the interference pattern of the light. The change is small, the measurement is exact, but to isolate this signal, the system must filter out every other vibration, from seismic activity to distant traffic. Even a truck passing 10 kilometers away produces noise that must be removed. Once the signal is confirmed, the implication is clear. Gravitational waves pass through matter without obstruction. They are not absorbed by dust or blocked by dense regions. They carry information directly from events that produce no light, or from regions where light cannot escape. This is not a refinement of vision. It is a new sense. Before that moment, in 2015, humanity had no direct way to observe these distortions. The universe was shaping itself in ways we could not register. Now, we are beginning to detect those changes, not by seeing, but by measuring how space itself moves as those events unfold. Between the stars, there is a region that appears silent, a vast interval where no obvious structure holds your attention, yet it is not empty in any meaningful sense. What fills it is known as the interstellar medium, meaning the diffuse material that occupies the space between stellar systems. It is thin, extremely thin. On average, this medium contains about 1 atom per cubic centimeter. By comparison, the air you are breathing holds roughly 10 to the 19 atoms in the same volume. The difference is so large that it is easier to think of interstellar space as almost nothing, yet even that near absence has structure. But it is not uniform. Within this sparse environment exist regions where density increases dramatically. These are molecular clouds, cold concentrations of gas and dust where the number of atoms can reach into the millions per cubic centimeter. Temperatures in these clouds can fall to around 10 Kelvin, just above absolute zero. In these conditions, motion slows, collisions become gentle, gravity begins to dominate. Over time, gas gathers. Regions within the cloud become denser, pulling in surrounding material. As the mass increases, pressure builds at the center. Eventually, temperature rises enough to initiate nuclear fusion, marking the birth of a new star. So even in the quietest regions, processes are underway. But the interstellar medium contains more than hydrogen and helium. It also hosts a range of complex molecules, some of which are familiar in entirely different contexts. In 1969, formaldehyde was detected in space, identified through its spectral signature. Later observations confirmed the presence of ethanol, distributed across large molecular clouds. Even glycine, the simplest amino acid, has been tentatively identified in several regions, suggesting that the chemical building blocks of life can form in environments far removed from planets. But one region stands out for its composition. The Sagittarius B, 2-molecular cloud, located near the center of the Milky Way, contains an enormous quantity of ethyl formate, a molecule associated with the scent of raspberries and the flavor of rum. The estimated mass reaches about 10 to the 33 kilograms, enough to fill a volume larger than the solar system. The implication is precise. The chemistry of space includes compounds recognizable at a sensory level, even if no human experience exists there to detect them. But motion continues through this medium as well. High-energy particles known as cosmic rays move through interstellar space constantly. These are primarily protons and atomic nuclei, accelerated to near the speed of light by energetic events such as supernova explosions. They pass through matter with little resistance. Even now, as you remain still, cosmic rays are moving through your body at a rate of about 1 per second. They leave no sensation, no visible trace, yet they are part of a continuous flow connecting distant events to local space. The silence between stars is not empty. It is active, structured, and filled with matter in forms that are easy to overlook, but essential to everything that follows. Step back far enough, beyond individual galaxies and their internal motion, and a larger pattern begins to resolve, one that is not obvious from within any single system. Galaxies do not fill space evenly. They arrange themselves into a structure called the cosmic web, meaning a vast network of filaments and sheets separated by enormous empty regions. The pattern is not random, it has geometry. Along the filaments, matter gathers. These regions act as channels shaped by dark matter, guiding the flow of gas and galaxies into long strands that stretch across millions of light years. Where multiple filaments intersect, nodes form, hosting the largest galaxy clusters known, bound together by gravity and embedded within extended halos of unseen mass. But between these structures lie voids. One of the most prominent examples is the Boötes void, identified in 1981. It spans roughly 330 million light-years in diameter and contains very few galaxies compared to surrounding regions. Within this volume, space approaches an extreme form of emptiness. But consider the implication. If our galaxy were located near the center of such a void, early observations would have revealed almost nothing beyond the local group. The nearest external galaxies would have been too distant for detection with 19th or early 20th century instruments. The broader structure of the universe might have remained unknown until much later. But even outside voids, the space between galaxies is thinner than the space between stars. In intergalactic regions, the average density drops to about 1 atom per cubic meter, compared to 1 atom per cubic centimeter within interstellar space. The difference represents a further reduction by a factor of 1 million. Yet this near emptiness is not uniform. Threading through the filaments is a component known as the warm, hot intergalactic medium, which is a diffuse plasma of ionized gas heated to temperatures between 100,000 and 10 million Kelvin. This gas does not emit strongly invisible light, making it difficult to detect directly, but it can be traced through its interaction with background radiation. It extends across vast distances, linking galaxies along the structure of the web. But its significance goes beyond distribution. Observations suggest that this diffuse medium contains a large fraction of the universe's ordinary matter, meaning matter composed of protons and neutrons. For decades, a significant portion of this matter was considered missing, not because it did not exist, but because it was too thinly spread to observe. Only in the 21st century did instruments become sensitive enough to begin detecting it. So the largest structures in the universe are defined not by dense regions alone, but by the contrast between presence and absence, between concentrated clusters and expansive voids. The pattern emerges through imbalance, not uniformity. But what appears empty still contains matter, energy, and motion distributed across scales that resist direct perception. The universe, at its largest, forms a network of almost nothing, connecting regions of something, all embedded within a framework that remains largely invisible yet defines the arrangement of everything we can observe. Imagine a single packet of light beginning its journey not in open space, but deep inside a star where escape is not immediate, but delayed by an almost unimaginable struggle. In the sun's core, a photon is created during nuclear fusion, then trapped within a dense plasma where it scatters, absorbed, and re-emitted countless times in a process called a random walk, meaning its path is constantly redirected with no straight escape. Progress is slow, extremely slow. It can take around 100,000 years for that photon to finally reach the solar surface, stepping outward through layers of matter only a fraction of a millimeter at a time on average. But once it emerges into space, everything changes. The same photon now travels freely, crossing the 150 million kilometers to Earth in about 8 minutes and 20 seconds. From that moment, its fate becomes immediate. When it reaches your eye, it does not linger or reflect. It is absorbed by a photoreceptor cell, either a rod or a cone, where its energy triggers a chemical reaction that converts light into an electrical signal. That signal travels along neurons into the brain. The photon itself is gone. Its existence ends at the moment of detection. Every photon you have ever seen has ended this way. But most photons are never seen at all. Many travel through space without ever encountering matter, crossing distances that extend beyond imagination. The universe, though filled with structure, is transparent enough that light from distant galaxies can move largely unimpeded, even across billions of years. Some of that light is still arriving. Photons emitted more than 13 billion years ago, during the early formation of galaxies, continue to reach us today, stretched to longer wavelengths by the expansion of space itself. This stretching is called redshift, where light shifts toward lower energy as space expands during its journey. But there is a limit. As cosmic expansion accelerates, regions of space beyond a certain distance begin to recede from us faster than light can travel. This boundary is related to what is called the Hubble radius, currently around 14 billion light-years. Beyond it, the expansion of space itself outpaces the forward motion of photons. Light can be sent toward us and still never arrive. Those photons lose ground over time, carried backward by the expansion of the space they are trying to cross. Their journey becomes endless, not because of obstruction, but because the destination continues to move away faster than they can advance. But this is not a distant abstraction. Over extremely long timescales, this effect reshapes the sky itself. In roughly 150 billion years, every galaxy outside our local group will have receded beyond this horizon. Their light will no longer reach us, not dimmed, not delayed, gone entirely from view. What remains will be local. The Milky Way and Andromeda will have merged into a single galaxy, surrounded by darkness that contains no visible trace of anything beyond. Future observers, if they exist, will see a universe that appears isolated and finite, with no evidence of expansion, no visible galaxies beyond their own. But the rest of the universe will still exist, beyond reach, its light continuing outward, never to return. A lens does not expand the universe. It exposes the limits of the observer. What changes is not what exists, but what we are able to register, as if each new instrument quietly redraws the boundary of what counts as real. You begin to see a pattern forming, not in the sky, but in us. In 1609, a simple refracting telescope revealed 4 small points orbiting Jupiter, now known as the Galilean moons, bodies that had circled unseen for all of human history until magnification made them undeniable. They were not hidden. We were unprepared. The lesson deepened, slowly. In 1781, William Herschel identified Uranus, a planet visible to the naked eye, yet mistaken for a star for centuries because its motion was too subtle to notice without careful tracking. Detection required patience, not proximity. It required attention shaped by tools. But sometimes even sight was not enough. In 1846, astronomers noticed irregularities in Uranus's orbit, deviations that could not be explained by known bodies. Using Newtonian gravity, they calculated the position of an unseen planet whose mass would account for the disturbance. When telescopes turned to that predicted point, Neptune was waiting. It was found before it was seen. But discovery could also be slow, almost meditative. In 1930, Clyde Tombaugh compared pairs of photographic plates, images of the same region taken days apart, searching for a faint object that shifted slightly against a fixed star field. After examining around 150,000 plates, he identified Pluto, a distant world revealed not by brightness, but by motion. The method mattered more than the object. But as distances increased, even motion and light became insufficient. Around other stars, planets do not reveal themselves directly. Instead, astronomers measure a transit, a tiny dip in brightness when a planet passes in front of its host star, often less than 1% of the total light. This requires precision beyond human perception, a sensitivity to variation too small for unaided vision. We detect absence as evidence. By 2024, more than 5,600 exoplanets had been confirmed using such techniques, and statistical analysis from missions like Kepler suggests that planets may outnumber stars within our galaxy. The sky we once believed sparse now appears crowded beyond expectation. But each expansion comes with a quiet correction. Every generation inherits a universe defined by its instruments, then learns that definition was incomplete, not incorrect, but partial. The boundaries shift outward, and what once seemed empty fills with structure, then complexity, then entirely new categories of existence. And the pattern does not suggest an endpoint. It suggests continuation. We build devices to extend sight, then discover that sight was never the primary limitation. It was interpretation. It was sensitivity. It was the narrowness of what we believed could be measured at all. With each new method, not just sharper lenses, but new ways of detecting light, motion, and gravity, the universe responds by revealing more than expected, but never everything. There is no indication that the current boundary is final, only that it is temporary, a horizon defined not by the universe, but by the present reach of human understanding. Before any star existed, before any galaxy traced a pattern across space, the universe entered a long interval where structure had not yet ignited into light. After the earlier glow faded and matter settled, what remained was a vast field of neutral hydrogen. Atoms formed when protons and electrons first combined, drifting and cooling as expansion continued. This period is called the Cosmic Dark Ages. For roughly 380 million years, there were no stars to shine, no galaxies to illuminate distance, and no sources of visible light that a human eye could ever detect. The universe was not empty, but it was visually silent, filled with gas that absorbed and scattered shorter wavelengths, leaving no clear path for brightness to travel. Dark, but not inactive. Gravity continued to work quietly within that darkness, drawing slightly denser regions of hydrogen together over immense timescales. These growing concentrations formed the seeds of the first stars, regions where pressure and temperature slowly increased until a critical threshold was reached and nuclear fusion began for the first time. The first stars were unlike any we see now. They are known as population 3 stars, meaning the earliest generation formed from primordial material containing only hydrogen and helium, with no heavier elements such as carbon or oxygen. Without those heavier elements to regulate energy flow, these stars are predicted to have grown extremely large, possibly hundreds of times the mass of the Sunday. They burned intensely, briefly. With such mass came extreme temperatures and rapid fuel consumption, limiting their lifespans to only a few million years. But during that short existence, they produced enormous amounts of ultraviolet radiation, a form of light more energetic than visible wavelengths. That radiation changed everything. As ultraviolet photons streamed outward, they began to ionize the surrounding hydrogen, meaning they stripped electrons from atoms and transformed neutral gas into charged plasma. This process, called reionization, gradually altered the transparency of the universe, allowing light to travel more freely across expanding distances. It did not happen all at once. Instead, small regions of ionized gas formed around each star or group of stars, creating expanding bubbles of transparency within the otherwise opaque hydrogen fog. Over hundreds of millions of years, these bubbles grew, overlapped, and eventually merged into a continuous, transparent medium. The universe became visible again, but the first stars themselves are gone. None have ever been directly observed. They lived too early and too briefly, leaving behind no surviving examples. Their existence is inferred from models of stellar physics and from the chemical signatures detected in later generations of stars, traces of heavier elements forged in their short, intense lifetimes. But their absence is not permanent. Modern instruments are beginning to approach the limits required to observe this transition period directly. The James Webb Space Telescope, launched in December 2021, is designed to detect extremely distant objects whose light has been stretched into infrared wavelengths by cosmic expansion. In that faint, red-shifted glow, we may begin to see the earliest galaxies assembling, and within them, indirect evidence of those first stars that ended the long darkness. We begin not by looking outward, but by reconsidering the star that defines our entire frame of reference, the one so familiar that it rarely feels mysterious. When you see the sun as a smooth, bright disk, you are not seeing a solid surface at all, but a layer called the photosphere, the region where hot plasma becomes thin enough for light to finally escape. It is a boundary of visibility, not structure. Below that layer, the sun is opaque. Photons cannot pass freely, and direct observation becomes impossible. Instead, we study its interior using helioseismology, a method that tracks pressure waves moving through the sun, much like earthquakes reveal the internal structure of Earth. These waves slightly shift the surface, allowing us to infer conditions deep within. We listen to the sun to understand it. But above the photosphere, something stranger unfolds. Extending millions of kilometers outward is the corona, the sun's outer atmosphere, visible during total solar eclipses as a faint, glowing halo. Despite being farther from the core, this region reaches temperatures between 1 and 3 million Kelvin, far hotter than the photosphere below, which sits at about 5,778 Kelvin. This inversion remains unresolved. According to basic thermodynamic reasoning, heat should decrease with distance from the energy source, yet here, the outer layers are hotter than those beneath them. Several mechanisms have been proposed, including magnetic reconnection, where tangled magnetic fields snap and release energy, and wave heating, where oscillations transfer energy upward. But no single explanation is complete. The sun, when observed beyond visible light, reveals a far more active nature in ultraviolet and X-ray wavelengths. Its surface appears turbulent, marked by loops, flares, and sudden eruptions. These events release solar energetic particles, high-speed streams of charged matter, and coronal mass ejections, vast clouds of plasma that can contain billions of tons of material. They move with immense speed. Some of these ejections travel at up to 3,000 kilometers per second, carrying magnetic fields that interact with planetary environments. When directed toward Earth, they can compress our magnetosphere and induce electrical currents across large regions of the planet. This has happened before. In 1859, a powerful solar event, now known as the Carrington event, reached Earth and produced effects that extended far beyond observation. Telegraph systems, the most advanced technology of that time, experienced surges strong enough to ignite fires in wiring. Operators reported receiving shocks, and in some cases, messages were transmitted even after power supplies were disconnected, driven entirely by induced currents. The sky changed as well. Auroras, typically confined to polar regions, appeared near the equator, illuminating night skies in areas that had never recorded such displays. The interaction between solar output and Earth's magnetic field became visible on a global scale. But today, the implications would be different. Our infrastructure depends on satellites, power grids, and communication networks that are sensitive to such disturbances. A similar event now could disrupt systems across continents, not through direct impact, but through invisible interactions between charged particles and electromagnetic systems. The sun remains constant in presence, but not in behavior. What appears steady to the eye conceals layers of complexity, energy, and instability, detectable only when we look beyond visible light into wavelengths that reveal motion, heat, and force hidden beneath a familiar glow. Instead of moving outward, we turn in the opposite direction, into a scale so small that ordinary language begins to lose its grip on description. Here, distance shrinks beyond intuition, and what seems solid dissolves into structure separated by vast emptiness relative to its size. Begin with the simplest atom. A hydrogen atom measures about 1/10 of a nanometer across, meaning 10 million of them placed side by side would span a single millimeter. That seems small until you look closer. The atom is not a compact sphere, but mostly empty space, with a central nucleus and a surrounding region where an electron is likely to be found. The nucleus is almost nothing in size. If you scaled a hydrogen atom to the size of a football stadium, the nucleus, a single proton, would sit at the center as a grain of sand. The rest of the space would be occupied by probability, a region where the electron does not orbit like a planet, but exists as a distribution of possible locations. Position becomes uncertainty. Within the nucleus, the structure deepens. Protons and neutrons are composed of quarks, fundamental particles bound together by the strong nuclear force, a force that operates only at extremely short distances but is powerful enough to hold atomic nuclei together against internal repulsion. Quarks have no measured size. Experiments suggest they are smaller than 1/10 million trillionth of a meter, a scale so far removed from direct experience that it can only be approached through indirect measurement. At this level, the rules of physics change. Quantum mechanics governs behavior, describing a world where certainty is replaced by probability. Particles exist in superposition. This means a particle can occupy multiple states at once until an interaction forces a single outcome. Entanglement allows two particles to share a linked state, so that measuring one instantly determines the state of the other, regardless of distance. Tunneling permits particles to pass through barriers they do not have enough energy to overcome in classical terms. But even the emptiness is not empty. Quantum field theory describes space itself as filled with fields that fluctuate continuously, producing pairs of particles and antiparticles that appear briefly and then vanish. These are called virtual particles, and though they cannot be observed directly, their effects can be measured. One such effect is the Casimir force. When two metal plates are placed extremely close together in a vacuum, they experience a small attraction caused by differences in quantum fluctuations between the space inside and outside the gap. This measurable force demonstrates that even the most perfect vacuum contains energy. But this idea does not remain confined to the microscopic. Some theories suggest that this vacuum energy may relate to dark energy, the large-scale phenomenon driving the acceleration of cosmic expansion. The same underlying structure that governs the smallest measurable scales may also influence the largest. The directions meet. As we move inward, the universe does not become simpler. It becomes stranger, revealing that the concept of emptiness, whether between galaxies or within atoms, is not absence, but a field of activity too subtle for direct perception, yet fundamental to everything that exists. If you trace the matter within your body backward through time, it does not remain local or even planetary, but disperses into events that unfolded long before the sun existed. The elements that compose you carry histories that extend across multiple generations of stars, each one contributing a layer of structure to what you are now. It begins with simplicity. In the first few minutes after the Big Bang, conditions allowed only the formation of the lightest elements, primarily hydrogen and helium, in a process called nucleosynthesis, meaning the creation of atomic nuclei under extreme temperature and pressure. These elements formed the raw material of everything that followed. But complexity required stars. Within stellar cores, hydrogen fused into helium, releasing energy that sustained the star against gravitational collapse. As stars aged, they began fusing heavier elements, forming carbon, oxygen, nitrogen, and beyond, building the periodic table step by step through successive fusion stages. This process shaped the chemistry of the universe. But there is a limit. Fusion inside stars can only proceed up to iron, an element whose formation no longer releases energy. Beyond that point, creating heavier elements requires conditions more extreme than even the most massive stars can sustain during normal lifetimes. But the universe provides those conditions. When massive stars end their lives in supernova explosions, or when neutron stars collide, densities and temperatures rise high enough to drive rapid neutron capture, a process where atomic nuclei absorb neutrons and transform into heavier elements such as gold, platinum, and uranium. These events are brief, but transformative. In 2017, detectors registered gravitational waves from a neutron star merger located about 130 million light-years away. This event, known as GW 170817, was followed by a kilonova, an explosion visible across multiple wavelengths, where heavy elements were formed and dispersed into surrounding space. That material did not remain isolated. Over time, it mixed into interstellar clouds, contributing to the composition of new star systems. About 4.6 billion years ago, our solar system formed from such a cloud, enriched by countless prior events, each leaving behind a chemical signature embedded in dust and gas. You are part of that inheritance. The calcium in your bones, the iron in your blood, and the oxygen you breathe all originated within stars that no longer exist. Their internal processes, sustained over millions or billions of years, produced the atoms that later became part of planets, oceans, and living systems. But some elements carry more violent origins. Gold, for example, is not formed in ordinary stars. It requires collisions between neutron stars, events that compress matter beyond the density of atomic nuclei. The presence of such elements within Earth's crust reflects a chain of processes that spans stellar evolution, explosive synthesis, and eventual incorporation into planetary material. Nothing in you is isolated. Each atom has passed through multiple environments, from stellar cores to interstellar space, from collapsing clouds to planetary surfaces. The matter you are made of has been assembled, dispersed, and reassembled across vast stretches of time. The connection is not symbolic, it is physical, traceable through measurable processes that link your composition directly to specific mechanisms within stars. What you are is not separate from the universe, but a continuation of it, structured by the same forces that shaped galaxies and ignited the first light. Long before instruments extended vision, the sky served as both map and mystery, a fixed reference that shaped how you and every human before you understood direction, time, and place. It did not change within a lifetime, and so it became a constant against which all motion was measured. You could navigate by it. For hundreds of thousands of years, human societies watched the stars with careful attention, learning patterns that repeated with seasonal precision. Constellations rose and set in predictable cycles, marking migrations, harvests, and the passage of time. The heliacal rising, meaning the first visible appearance of a star just before sunrise, signaled transitions that could define entire calendars. The sky became a tool. One of the earliest known attempts to represent that sky in physical form appears in the Nebra sky disk, dated to around 1600 years before the Common Era. This bronze disk, about 30 centimeters wide, carries gold inlays that correspond to the sun, the moon, and a cluster of stars identified as the Pleiades, arranged with an intention that reflects both observation and meaning. Knowledge was embedded in objects. Across continents, cultures developed their own systems of interpretation. Aboriginal Australian traditions, extending back at least 10,000 years, incorporate detailed knowledge of stellar movement woven into oral narratives that encode navigation and ecological awareness. In Mesopotamia, Babylonian astronomers recorded star positions with a precision that remains recognizable to modern analysis. The sky was shared, but understood differently. But for all this attention, the nature of the stars remained uncertain. They appeared as points, unchanging and unreachable, embedded in a fixed dome that defined the boundary of the world. Their distance was unknown, their composition unimaginable. Then the interpretation shifted. In the late 16th century, Giordano Bruno proposed that the stars were not lights fixed in a celestial sphere, but distant suns, each potentially surrounded by its own planets. This idea extended the structure of the solar system outward, transforming isolated points into systems like our own. It was a radical expansion. Bruno's view was not accepted in his time, and in 1600 he was executed, partly for ideas that challenged established cosmology. But the concept persisted, supported later by telescopic observation and the development of stellar physics. It became the foundation of modern understanding. Now we know that each visible star is a source of energy comparable to the sun, often larger, often older, and frequently accompanied by planetary systems. Many of those planets exist within regions where temperatures could allow liquid water, conditions that, in our case, support life. The implication is quiet, but significant. Other skies may exist. But even with this knowledge, the experience of looking upward remains similar to what it was for the earliest observers. The stars still appear as points against darkness, their true nature hidden by distance and scale. The difference lies not in what you see, but in what you understand about what is there. The questions have not disappeared. They have expanded. As explanations deepen, they reveal further layers of complexity, and each answer leads outward, not toward closure, but toward a wider field of inquiry that continues to grow beyond the limits of any single perspective. You return to the image that began this quiet question, a horizon without stars, a frame where absence seemed to dominate what should have been filled. But now the absence feels different, not an error in the scene, but a limitation in the way it was captured, a narrowing of what could be recorded at that moment. The darkness is not a mistake. Those photographs taken on the moon do not show a missing sky, but a sky overwhelmed by brightness, where the camera chose one range of light and excluded another. The stars did not vanish. They remained present, simply beyond the sensitivity of the settings used to preserve the foreground. But that small example reflects something much larger. What you can see, even with the most advanced instruments, represents only a fraction of what exists. Dark matter and dark energy together account for about 95% of the universe's total content, yet neither has been directly observed through emitted or reflected light. Their presence is inferred, measured through effects, but never seen in the way ordinary matter is seen. The majority remains hidden. Even within the light, we can detect. Visible wavelengths occupy less than 1/100% of the full electromagnetic spectrum, the entire range of possible light. Beyond that narrow band exist radio waves, infrared, ultraviolet, X-rays, and gamma rays, each revealing structures that would otherwise remain unknown. Vision is selective, and light itself is not the only messenger. Neutrinos pass through matter almost without interaction, carrying information from dense environments light cannot escape. Gravitational waves ripple through space-time, recording collisions between massive objects without distortion from intervening matter. There are multiple ways to know, but each requires its own instrument, its own method of interpretation, and each reveals only part of the whole. The picture grows, but never completes. With every expansion, new limits appear, not as failures, but as edges waiting to be crossed. This pattern has never reversed. Every generation has inherited a sky that seemed complete, then discovered it was partial. The process continues. The James Webb Space Telescope now observes galaxies forming earlier than expected, suggesting that the current models of cosmic evolution are incomplete. The universe is assembling structure faster than predicted. Understanding adjusts to match reality, but the adjustment is ongoing. You are here, within a narrow band of perception, surrounded by layers of phenomena that extend beyond direct awareness. The darkness around you is not empty space, but a field dense with signals, histories, and interactions that require translation into forms you can perceive. The silence carries information, and the absence of visible stars in that original image becomes something else entirely, not a contradiction, but a clue. It points toward the limits of capture, the boundaries of detection, and the quiet presence of everything that lies beyond those boundaries. The universe does not withhold itself. It presents more than can be taken in at once. So the darkness remains, not as a void, but as an invitation, a space where what is unseen is not gone, only waiting for a way to be revealed, as it has been, slowly and steadily, across every step of the human attempt to understand it.